Welcome to a discussion with Ruth Durrer regarding testing general relativity with cosmological large scale structure. This discussion will be focused on how we can test general relativity to make sure that it's also applicable in the cosmological domain. Hope you enjoy that. So, a good starting point then, I think, would be to talk a bit about the background for why this paper is relevant. I'm thinking specifically around testing of general relativity that this relates to, and if you would mind stepping through some of the history regarding that, why is it an active space of investigation, let's say, to see how we can test general relativity if it's already more or less an accepted framework? Have we not tested it in the past?
Of course, we have tested it, but physical theories always work on a certain range of scales and energies. And in a certain range, all physical theories which we know so far have their limitations. So it would be interesting. It is always interesting to test theories in different setups. If you test it in one situation, it might be violated in another situation. That's physics, right? We rely on experiments, on an experimental testing of our theories in all possible ranges.
Mhm.
Now, in cosmology is in that sense different from what we have done so far. One has, for example, light deflection around the sun, Shapiro time delay, all possible things which have been tested in the past, mainly are tests actually of the vacuum Einstein equation. Namely, they test the so-called Schwarzschild solution of general relativity, which is a vacuum solution, or also gravitational waves, which have been discovered, are vacuum solutions. Cosmology
Mhm.
is not a vacuum solution. There is a energy density and a pressure typically, which play a role, which give a right-hand side to Einstein's equation. This is one thing which is different in the
Mhm.
cosmology setup.
Mhm.
And of course, the second one, which is equally relevant, is it tests general relativity on much, much larger scales.
Mhm.
Even though we always thought that general relativity will break down only on very, very tiny scales, much smaller than scales which we can test so far. Who knows? Maybe there might be something on large scales. So let's test it also on very large scales, and that's cosmology, which can do that.
Mhm. If we linger then on the breakdown between this vacuum solution and then the general case, when would you say either is applicable? So maybe more specifically, when is the vacuum solution to this applicable?
If there is no matter around. For example,
Mhm.
we test general relativity if we look at its test in the solar system only outside the sun, where the universe is more or where we can have the vacuum of the Friedman solution. The Friedman solution is actually a vacuum solution, right? And so,
Mhm.
and sorry, I wanted to say Schwarzschild. The Schwarzschild
Okay.
solution is a vacuum solution of Einstein's equation.
Mhm.
And we test only the Schwarzschild solution. So that's the solution of the sun, of the gravitational field of the sun, outside of the sun, not inside.
Mhm. Mhm. And how do we test that currently? I know that's not part of the paper per se, but
Yeah,
just to
yeah,
set
but
the
there are
stage.
via light deflection, via lunar ranging, ranging lasers up to the moon and back.
Mhm.
There is a time delay of these lasers due to the gravitational field of the sun and of the Earth. These are all vacuum fields.
Mhm.
But we have also much stronger tests by looking at pulsars. These are white dwarfs or neutron stars which rotate around each other and which send to Earth very, very regular pulses, which are affected by the gravitational fields around these pulsars.
Mhm. And
Uh,
I take it then that it's more complicated to test this in a cosmological setting. Would you mind shedding some light on why? Why is it more difficult to test that? Why would the standardized test that we've used for locations where the vacuum solution is applicable not be transferable, let's say, to the other cases?
um, we don't have cosmological observations which are sufficiently accurate to do anything like that.
Okay.
In cosmology, our accuracy is probably at the percent level. So we would need to, we can test it, we can test general relativity there at the percent level. And you see on cosmological scales, the universe is statistically homogeneous and isotropic. So all these things like, for example, light deflection, which is one of the tests which we want to do on cosmological scales, is a statistical effect. We have to look at statistics. We don't have single objects like the sun or a pulsar or so in cosmology. We look at statistics.
Okay. And at the current moment, do we have any tests that at least strengthen the hypothesis that general relativity is applicable to that domain as well? So,
Absolutely.
and
Absolutely. We
yeah.
have several. So far, all cosmological observations which we have made so far are kind of in agreement with general relativity. On the other hand, we must say we have introduced two new components of matter in cosmology, namely dark matter and dark energy, which we haven't seen in any other way than via their gravitational effects. And by calculating how much dark energy and dark matter we would need, we assume that general relativity is correct. So there in cosmology, it goes a little bit sideways. We assume these new dark matter and dark energy, which have specific properties, to uh, to satisfy Einstein's equation.
Right.
Afterwards, we calculate, we go on and calculate, for example, what would be a new observation like gravitational lensing, exactly this light deflection, assuming that these dark matter and dark energy are there, and we find agreement.
Okay. And my understanding in the cosmological case is that the Einstein equations then collapse into the Friedman equations or simplify into the Friedman equations. So in effect, those are the ones that we're interested in testing then with these specific tests.
Uh, we go a little bit beyond the Friedman equations, right? The Friedman equations are those which are Einstein's equations in a perfectly homogeneous and isotropic universe. Now we know there is structure in the universe. There are galaxies, there are galaxy clusters, and so on. And then we assume that these are relatively small perturbations with respect to the mean density, matter density of the universe. And but we take those into account. So not just the Friedman equations, but the Friedman equations plus perturbations.
Okay.
Here you
Okay.
have the Friedman equations, the homogeneous cosmology, and then we go on, and not yet here, I think a bit further down. Yeah, we will allow for perturbations, large scale structure. These are the structures. Once these are the perturbations as we would observe them, assuming that there are perturbations in the metric, and they satisfy the perturbed Einstein equations, which are then more complicated than just the Friedman equations, where we have a spatial dependence as well.
Okay, so if we focus on this equation 11, because I think it recurs in the paper as well,
Yeah.
would you mind elaborating a bit further on what this actually
Okay.
represents?
This equation here tells us if you look into the sky and you count galaxies and you look at the fluctuations of that count, so you subtract the mean, you count your galaxies in a given direction, in a certain patch, in a given direction at the given observed redshift Z, then this has different contributions. The first term, I don't know whether you see my pointer, probably not.
No, I don't see it.
Yeah, is a density term. That's this first term. Then come other terms from the velocity. V is the velocity potential. which lead to so-called redshift space distortions, especially this last term on the first line is such a redshift space distortion.
Mm-hmm.
Yeah, I see your point, probably coming to the last term, maybe. Then another term which is important is the first term on the last line. This is exactly such a lensing term. That's exactly deflection of light from lensing. So if there is more like, for example, if I'm looking at the number of galaxies in a given patch, and in the
Mm-hmm.
foreground I have a lot of matter, then light will be deflected, and I have the impression that these number of galaxies come from a larger patch, and I give them a lower density. And
Mm-hmm.
then there is another effect which to some extent compensates that, which is if I have, and whatever telescope I have, it will have some kind of luminosity limit. A galaxy must have a certain flux so that I can see it in my telescope.
Mm-hmm.
Now, if I have matter in front of a background galaxy, its flux will be collimated and I will get more of the flux into my telescope, and I see galaxies which I would not have seen, uh, uh, wouldn't be this cluster of galaxies in front of it. This gives
Mm-hmm.
this integrated effect.
Mm-hmm.
Then the last effect is the so-called Shapiro time delay effect, which also is present. And there are other effects which are all have to do with the geometry and the change of the geometry along the path of the photon. Um, these Greek letters phi and psi here actually are the perturbations in the metric.
Mm-hmm.
The d is the density fluctuation and v is the velocity.
Okay.
And this h and so are the Hubble parameter and so. To derive this equation, that's a bit lengthy and rather technical thing to do. But once
Mm-hmm.
you have them, you see that you have in this equation, on the one hand, I think that's probably the most important for non-experts, you have components of energy and momentum, namely density and velocity, and
Mm-hmm.
you have components of the metric. So in principle, if you can to some extent isolate those components, you can test both the energy momentum tensor, so the energy density and the velocity, and on the other hand, the metric. And if you have these both things, you can test Einstein's equation because they
Mm-hmm.
are relations between the metric perturbations, the metric, and the energy and the momentum of your
Mm-hmm.
of the matter distribution. So in
Okay.
principle, with this equation, if we can, and we can actually isolate to some extent this last term and the first term, which are very important, and we can measure this lensing term here. The others are really small and are very difficult to measure. It's not clear whether we will ever be able to measure them.
Mm-hmm.
We will have to develop new methods. But already, if we can measure the velocity term here and the density term, which is the first term, and this lensing integral,
Mm-hmm.
would in principle allow us to isolate metric perturbations and energy momentum components, which can help us to test Einstein's equation.
Mm-hmm. If we think for a second more about the derivation of this equation, not the technical details associated with it, but just the conceptual fact that we're adding a perturbation now to compensate for the fact that our universe has some structure, is there a way to think about how you introduce that information into the system? So we have some structure in the universe. How are we perturbing the equations conceptually um, to introduce that? Do we have some notion of how much the universe deviates from uh, well, yes,
Yes,
for
we
yeah.
have
Mhm.
we have a rather good knowledge of the initial perturbations because we have the cosmic microwave background fluctuations, which are very well measured, and we
Mhm.
can compute those. And we know, therefore, what the initial metric perturbations are, what their spectrum was. The spectrum means the amplitude of the fluctuations on a given scale, on a given for a given wavelength scale. That we know rather well through the cosmic microwave background. The
Okay.
cosmic microwave background is this relic radiation from the Big Bang, which also has small fluctuations, which have been extremely well measured. So we know relatively well the fluctuations of the metric, so these phi and psi, we know them relatively well, I mean statistically. And if Einstein's equation holds, they give us both d and v. So we can then go and see whether that's the d and v which we really measure.
Okay. So when it comes then to actually going out experimentally and verifying what we see in these equations, what are some of the complications when it comes to that at the
Yeah.
moment? So yeah.
For example, one complication is that this d, the first term, this has this factor b in front of it, which means what Einstein's equation feel is the density fluctuation. What we see are galaxies. And they are what we call a biased tracer of the density. Of course, you can imagine where there are more galaxies, there is more matter density. But how exactly are these related? Here we make a very simple assumption that on large enough scales, we can assume that the relation is simply linear. And we can also kind of measure this bias factor B. That's one of the complications. Another complication is that this equation 11, as it is written here, only assumes linear perturbations. So it assumes that all the perturbations are much smaller than, for example, the density perturbations are much smaller than the mean density. On small scales, this is not true. On large scales, however, we hope that to be a reasonably good approximation. Now, do the small scale fluctuations really average out on large scales? And is there no influence of these small scale fluctuations to the large scales? This is not entirely clear.
Okay.
So these are two of the
Is
difficult.
there a way to potentially get some clarity in how large those deviations are on a large scale now?
Yes, I think we already have some indication that we are reasonably okay on large scales because we have already some galaxy catalogs and we can calculate the density fluctuation spectrum from them, and it reasonably agrees via Einstein's equation with what we expect. But the moment we want to be more precise, we don't know whether we will be limited by this effect. It's reasonably okay now, so at the few percent level, but now we want to go to 1% or even below. Whether it then still holds is not clear.
Okay. So then, under the assumption that we simply associate the number of observed clusters with the density, how would we then go about testing this? So experimentally now, what would be sort of a setup that we could use to find an answer to this question?
Okay. One possibility is to measure the masses via assuming exactly that the density and the number of galaxies are kind of simply related, or then measure it via lensing. Lensing really measures the total mass. So if we often do that with galaxy clusters, that we measure their mass in different ways via lensing, via their luminosity, etc. And we see whether this linear bias holds. And for galaxy clusters, I think it doesn't hold very well. But nevertheless, galaxy clusters are on the scale of 1 megaparsec, which is about 3 million light years. And that's cosmologically speaking a relatively small scale. We hope this to hold on the level of about 10 megaparsec. So what we do there to test it is numerical simulations.
Mm-hmm.
And there it seems to hold really well,
Okay.
reasonably well.
Okay. Mm-hmm. But then when it comes to, let's say, conducting an experiment and getting measured numbers on this, you mentioned lensing as one approach. Could we go into some more detail on how that works and how you get an approximation then for the density through that?
Okay. The lensing, you do it in the, you see, for example, let's talk about lensing from a cluster.
Mm-hmm.
You look at background galaxies, galaxies which are at higher redshift, so behind that cluster,
Mm-hmm.
and their light is deformed due to the foreground cluster, due to this lens. And
Mm-hmm.
you can calculate, you assume that they are arbitrarily oriented, and you see
Mm-hmm.
that they will become oriented really kind of around the cluster. There are very nice pictures of this,
Mm-hmm.
which can be found on the internet. And from that, you can calculate what the deflection field should be, and that gives you kind of the mass of the cluster. All of what I'm saying is, of course, not the full story. In detail, it's always more complicated. You need a lens, so-called lens model for the cluster, etc., etc.
Mm-hmm.
But if you have lots of galaxies behind these clusters, let's say
Mm-hmm.
hundreds or so, then you can test your lens model relatively well, and you can get relatively good mass estimates
Mm-hmm.
with this lensing method.
Mm-hmm. And what is the reason why this kind of method has not been applied yet? That's my understanding, at least, that
It
this would
is
be a
applied.
new
It
kind.
is.
Okay.
No, 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 no,
Okay.
no. It is applied. It is
Mm-hmm.
applied for individual clusters.
Yeah.
But what I'm in this equation 11, this lensing, I consider not the lensing from an individual cluster, but from the large scale distribution in the universe in a statistical sense.
Mm-hmm. Okay. Okay.
So
And if we
it's,
then, yes, okay. If we then generalize it to that setting, what are the complications that are introduced at that point?
uh-huh. The complications are that it appears not as a single term, right, but only in
Mm-hmm.
this large sum. And so I have to know, how can I isolate this lensing term? And the best way to isolate it is if I now correlate number counts which are at higher redshift with number counts at slightly lower redshift.
Mm-hmm.
If I do this, then they have in common the entire light deflection which is in front from objects which are in front of them both. So they
Mm-hmm.
have this, and that's only the lensing which have the density fluctuations at lower redshift and at higher redshift are nearly uncorrelated,
Mm-hmm.
whereas the lensing is not uncorrelated. So this, we have simulated it with numerical simulation. One should be able to observe it, for example, with the Euclid satellite, which has been
Mm-hmm.
launched last summer.
Okay. Okay.
So
Uh,
data will soon be able to look into this, I think.
mm-hmm. Okay, understood. So I think there are three different kinds of measurements being outlined in the paper. We have number counts, intensity mapping, and shear measurements being referred to. So number counts, I believe we already touched upon that, and also intensity mapping. Would you mind just reiterating like what those measurements actually involve, just to make it clear, like
Mhm.
where we draw the line between one and the other,
Yeah.
and then maybe we can get into shear measurements as well.
Okay, so number counts is exactly this formula. You count galaxies in a patch on the sky at a given redshift. Now, intensity measurement, there you do not count individual galaxies, but you just look at the intensity of the flux of a given spectral line. One
Mm-hmm.
very beloved spectral line is the 21 centimeter line of neutral hydrogen. The reason that cosmologists like very much this line is that it is rather well separated, and secondly, 75% of the universe is hydrogen, so we have a lot of hydrogen. We can hope to see an intensity. So one would like to look at fluctuations of this 21 centimeter line. That's very difficult. The line has been seen already, but it has been correlated with number counts. That has been done with large error bars still, but the autocorrelation of the 21 centimeter line in a given direction and the given redshift here with the one in another direction or at another redshift here, that has not yet been achieved. The problem with this intensity mapping is there are, of course, lots of other sources which also emit photons with the corresponding wavelength, and you want only those from this very specific line. So you have to get rid of all these foregrounds, which are typically several orders of magnitude stronger than what you want to see. So that's the difficulty.
How do you approach that?
So one thing which I would say the most important thing is a line is very narrow, spectrally very narrow. So you only take light which is in this wavelength, but which drops down very, very strongly when you move a tiny little bit away from this wavelength. So that's the main way to distinguish it.
Don't you also have let's say in the foreground noise that is being also measured, things of exactly the same frequency?
Yes, you do. And actually several orders of magnitude more than what you want to see. So what you have to do is you go a little bit away from the frequency you're interested in, and you throw away everything which is still there, because you know
Yes.
your line is no longer there.
But you're then counting on there not being an exact match in terms of frequencies, like there is a small shift. So
No, most other sources are not line, but have a kind of continuum spectrum which is ranging over. You will not have another line exactly in your
okay.
but
Okay,
you
so you
will
wouldn't
have
call
some kind of continuum which will still be there when you go a little bit left and right.
Okay. Do you also compensate for the intensity of that, like on the exact spectral location of the line as well then? So the way I imagine this now, and please correct me if I'm being naive here, but you have some continuum from the foreground noise, and then you have one spectral line that's orders of magnitude smaller than your foreground noise. And then you would not only remove everything besides the specific frequency that you're looking for, but also for the specific frequency you're looking for, you would use the distribution of this continuum to try and compensate that away. Is that correct?
That's roughly it. That's
Okay.
roughly it. Honestly, this is an entire industry. I can't give you too much details about it
Yeah.
because I don't know them, not because I
Okay.
don't want, but I
Yeah.
think it's quite complicated. And yeah,
Mhm.
I mean, there are people who are much more expert on these experiments than I am. I'm actually a theorist, so I don't know exactly. I always wonder that they can see it at all. And yeah, I mean, I also think that there might be a couple of false positives in the literature about this, but yeah, it's
Okay.
still quite debated.
Is there anything else on intensity mapping that we should also discuss before going on to the shear measurements?
Maybe just that the intensity mapping have one advantage or disadvantage, depending on what you want. They don't have this lensing term, which we were discussing quite significantly, because you see, there is photon number conservation. You could say that with the intensity mapping, this kind of increase due to the fact that you see more photons, and the decrease due to the fact that you might see them coming from a wider area exactly cancels. That's a consequence of the conservation of the number of photons under gravity. You don't destroy or generate any photons. So if you correlate intensity mapping with galaxies, you can actually get rid of this lensing term, which is kind of interesting. So you
Hmm.
could have a measurement without the lensing term, and if you do the number counts alone, you have the lensing term. So
Hmm.
that would also be an interesting way to isolate this lensing term, which has been
Hmm.
studied in the literature, but not been done in practice so far. But
Uh-huh.
all this will be done in the next few years.
Okay, so that's also then from a, let's say, computational or experimental standpoint, feasible to correlate those. So in
Yes.
practice, or sorry, in theory, you could do it. Would it be possible to do it in practice as well if you wanted to do measurements on it, or is it too, let's say, complex of a task to do, practically speaking?
I think it will be done a little bit. People have already correlated a little bit number counts and intensity mapping, but on a much too kind of much uh, not precise enough way. I mean, we
Hmm.
will need much better precision on this. But I'm quite convinced that within this decade we will have them.
Hmm. I thought it would not be so much of a precision question as a, let's say, complexity question. I don't know how much, like, how many of these would need to be correlated, but don't you have noise from... So the way I'm naively thinking about this is you have a large number of sources of noise, and you would need to correlate, let's say, all of them. And depending on how large of a set you have, uh, those correlation matrices or whatever correlation values, if they grow to a very large degree, then wouldn't it be very computationally difficult to estimate that?
It's a computationally reasonable challenge, but no, there are much bigger challenges which have been solved.
Okay.
The more
Huh.
objects you have, the smaller becomes your noise, of course. The more objects you can do it on relatively large scales and so, but you do have to have a certain precision. You know, if an effect is a few percent, then your
Mhm.
precision you want to detect it at 5 standard deviations. So
Yeah.
your precision should be 0.5%, otherwise you will not see it,
Mhm.
right? So that's the precision question. These effects, which allow us to test general relativity, are typically on the few percent level, relatively small. So we need to have good precision to see them.
Mhm. Okay. Okay, very good. But then if there's nothing more to say about the intensity measurements, at least to give a general overview, then maybe we can go on to the shear measurements as well.
Sure.
Would you mind describing on a high level what those are and why they're relevant?
Okay, so as I already said before, the lensing allows us to really measure the mass without having this, we count galaxies and hope that the number of galaxies is in a simple way related to the total mass.
Hmm.
There you really measure deflection. What you do measure is actually deformation of galaxies. Galaxies are typically deformed by they change their ellipticity by about 1% due to the presence of
Hmm.
foreground lenses or
Hmm.
foreground matter. So this is very little. So you need to measure the shape of these galaxies very precisely. And you then have to correlate, if uh, if the shapes of galaxies at different redshifts are correlated, that's certainly not going to be an intrinsic correlation due to the way these galaxies formed, but most probably due to some foreground lens, which they
Hmm.
both have in front of them.
Hmm.
That's shear measurements. They have been done. We have the kids survey, um, uh, we have lensing from this. These are the latest ones. I mean, there are several lensing surveys which have been done and which have calculated this correlation function from lensing.
Hmm.
Now, what we also can do is correlate these shear measurements, so the galaxy shear, the deflection of galaxies. Galaxies are kind of torn apart. They are stretched in one direction and compressed in the other. That's what we call shear.
Hmm.
We can also look at the correlation of these shear with number counts. That has also been done. and this gives us a relatively good measure of the matter in the universe.
Why does it help to correlate it with number counts? What additional information do we get from that?
Um, One has different systematic errors, different statistical errors. It's not new or independent information, but it has different systematic errors, so you can beat down the error bars.
Mhm. Okay. And then going back to the assumption as well of correlations in the shapes between different galaxies or galaxy clusters, we're saying that that's much more likely to be, much less likely to be caused by an initial correlation in their shapes. Why are we saying that that is the case?
Okay, if galaxies are close to each other, they may well have formed from an initial very large scale fluctuation leading to galaxies which are kind of aligned in some way,
Hmm.
right? Have ellipticities which are kind of similar, kind of
Hmm.
aligned. If and this is what we call intrinsic alignment. That's the biggest unknown in all these shear measurements. That's the biggest difficulties to perform good shear measurements. One has to model this intrinsic alignment. But if you have galaxies at different redshift, one very, very far away from another one, it's very
Hmm.
unlikely that they have been formed by a similar process.
Hmm. Okay. Okay. Good. So then, zooming out again, now that we've described these three measurements, you said that you believe we will have measurements, let's say, in the next decade for some of these approaches. Um, do you see one of these that's more promising or more, let's say, short-term applicable compared to the others, where you think we're going to see the
Uh-huh.
first measurements?
I think I would put on the same level density, so number counts and shear measurements. We already
Hmm.
have quite an experience with them, and we will make the progress which is needed within the next few years. The line intensity measurements are more difficult, and it's not clear whether that will work, in my
Hmm.
opinion.
Okay. Okay. And is there anything that's stopping us currently from going out and doing these, let's say, shear measurements and number count measurements? Is it mainly in the precision that you mentioned before, that the current instruments that we have are, let's say, on the verge of not precise enough? Or what is sort of the boundary, if you will, that we're now crossing that allows us to do these measurements that we were not able to do before?
Mm-hmm. Okay, for shear, the biggest problem is not there are it's not the only, but there are several problems. For shear, it's the intrinsic alignment which is a problem. Now,
Hmm.
for both shear and number counts is the question how good can we model them? Linear perturbation theory, what I outline here in this paper, is
Hmm.
relatively well known and can be calculated, and we have code to calculate these spectra in a second. So that
Hmm.
problem is totally solved. However, on smaller scales, nonlinearities become important. There we do numerical simulations. If you only do dark matter and assume that the baryons behave in the same way kind of as the dark matter, then we also have relatively good simulations, even though they are costly and large. But now people are trying to model them, with
Hmm.
machine learning and so. Um, but the biggest problem there is on smaller scales, baryons probably behave differently. They have pressure, they emit radiation, and all of that is not very well modeled in these simulations. In the
Hmm.
baryonic simulations, they are very difficult, and people put in many parameters, and it's not clear how accurately they describe the true physics and whether we just can find out something about baryonic physics but not about cosmology on small scales.
Hmm.
On the other hand, if we have to throw away all the measurements on smaller scales, let's say scales below 5 megaparsec, then we throw away a lot of information because this information is there, and if we can interpret it, it would be
Hmm.
really interesting. but
Hmm.
I'm not sure whether we are able to.
Hmm. Okay. Looking forward then, with this line of research and these kind of measurements, are there any things on the horizon, let's say, that we're not able to do now when it comes to, let's say, simulation capabilities, for example, that you believe we will be able to do more accurately going forward?
Uh-huh. I'm not sure whether we will be able to do better simulations of baryonic physics. This is very, very difficult and very costly, and honestly, I don't believe it very much what people are doing because they just put in hundreds of parameters to, and then they adjust those parameters that the simulations so that the simulations produce what we see in the sky, but this doesn't help us to test anything, right?
Hmm.
So if you want to test anything, I'm not sure whether that's the way to go. But what I think might be interesting and where progress will be done in the simulations is to do higher order correlation functions like 3-point, 4-point correlation functions. And they contain also very interesting information also
Hmm.
about testing general relativity.
Hmm. Okay,
And there I'm sure progress is being made.
right. So then, generally with the paper, we touched upon some of the points here. Are there any things that you feel like we didn't touch upon that are important to mention with regards to the publication?
No, I think we went well over the paper. We even touched upon things which I didn't write in this paper because, as always, you can never be complete in such a paper.
Hmm.
So there I just really discussed three observations. Of course, what we didn't discuss so much are the small relativistic effects, which I said are going to be small. But
Hmm.
I think we don't really need to measure them in order
Hmm.
to be able to test Einstein's equation.
Okay, so the hypothesis is that they're not influential enough to really
Yeah,
cause significant
that
deviations.
they are probably on the per mil level, and our precision will, within the next few years, not go there,
Hmm.
I'm afraid.
Okay, but then as a conclusion to the paper and the discussion, is there anything additional that you would like to say? Maybe like requests from the research audience or the, let's say, research community, of things that are not being done, perhaps to the extent that you would like to see, or anything of the
Uh-huh.
sort.
Uh-huh. I think something which really will be important and is not totally planned to do is to correlate number counts at different redshifts. I think that will be, it's a very small signal, but if we can get that signal, that will really be an alternative to shear measurements, to
Mhm.
lensing, and we have derived an estimator for that signal. This would help us really to measure, to kind of um, measure the lensing potential at different redshifts.
Okay, and what is currently lacking, let's say, from that, or what's the challenge with introducing that at the moment?
Uh, this can be, this can probably not be done before we have really good Euclid data.
Hmm.
We made forecasts for the presently running DESI, and we don't think that DESI can actually do this sufficiently accurately to see a signal. You
Hmm.
know, there
Okay.
it's going to be buried in the noise, but Euclid should be able to see it.
Okay. Okay. Very good. But then, with that, if there are no additional concluding remarks, I would thank you very much for taking the time to chat about the paper.
Thank you. It was a pleasure.